Hello students, today we are going to discuss about interference in thin films. Interference in thin films from the chapter Wave Optics. Right? The topic name is interference in thin films. Right. Thin films are nothing but transparent materials. Thin films are nothing but transparent material having thickness vary from few nanometer to few micrometer. Okay, we know that 1 nanometer is equal to 10 power minus 9 meter and 1 micrometer is equal to 10 power minus 6 meter. The transparent material having thickness vary from few nanometer to few micrometer are called thin films. The best example for thin film is soap bubble. Right, the thin glass pieces. Thin glass pieces. Crack on the glass plate. Cracks on the glass plate, and oil spread over the water surface. Right? So these are some examples of thin films. Right? Or you understand what is meant by thin film? Thin film are nothing but a transparent material or the transparent materials having thickness vary from few nanometer to few micrometer. Okay, some of the examples of thin films are listed here. One is a soap bubble and thin glass pieces and cracks on the glass plate and oil spread over the water surface. Right. Sometimes we have seen dazzling colors or brilliant colors exhibited on the thin film, right? Exhibited on the thin film. Thin film, for example, the oil is spread over the water surface or always a soap bubble, right? So sometimes we have seen some colors exhibited on a soap bubble and on the oil surface. Spread over the water surface, right? So these colors are due to the interference of light waves. The interference of light waves which are reflected from top and bottom surface of the thin film. Right? Suppose this is a thin film. When the light is incident on this thin film, a part of the light is reflected from the top surface and the remaining part is reflected from the bottom surface. Okay? When these two waves are interfere to each other, then there will be a color is formed. Okay, color will be formed. So the existence of brilliant colors on the soap bubble and oil spread on the water surface are due to the interference of light waves which are reflected from top and bottom surface of the thin film. Right? And the nature of the colors or the colors is depends on three factors. One is the thickness of the thin film. So depending upon the thickness of the thin film, the colors formed by these two interferent waves will be changed. Right? So one is the thickness of the thin film. Second one is the refractive index of the material of the thin film. And the third one, the angle of incidence of the light on the thin film. Right? So there are three factors. Okay. Depends on the colors exhibited, the nature of the colors exhibited on thin film. One is the thickness of the thin film, second, refractive index of the thin film, and the third one, angle of incidence of the light on the thin film. So, right? The colors formed on the thin film depends on three factors: thickness of the thin film, refractive index of the thin film, and third one is the angle of incidence of the light. Right? Okay. So already I told, if any white light is instant on any one of the thin film like soap bubble or the oil spread over the water surface, the colors are exhibited on it. Okay, which is due to interference of light waves which are reflected from top and bottom surface of the thin film. Which are reflected from top and bottom surface of the thin film. And the colors depends on the thickness of the thin film, and the refractive index of the thin film, and the last one, angle of incidence of the light on the surface. Angle of incidence of the light on the surface. Right. Now let us consider a thin film of transparent material. Thin film of transparent material bounded by two surfaces, that is upper surface and bottom surface. Upper surface and bottom surface. And suppose the thickness of the transparent thin film is taken as D. Right? So this is a thin film of a transparent material whose thickness is D. Right? And the refractive index of this thin film is taken as mu. So mu, refractive index of the given thin film, and its thickness is D. And this is bounded by two surfaces. One is a top surface and another one is a bottom surface. Top surface and a bottom surface. Right. Now, a beam of light is instant on this thin film at a point A on its top surface. Right, on its upper surface or top surface, there is a beam of light which is instant at point A on the top surface of the thin film. Top surface on the thin film, right? And this ray is divided into two parts. So when the beam of light is instant on the top surface of the thin film at point A, it is divided into two parts, right? One part of the light is reflected from the surface of the thin film. Right, one of the part is reflected from the top surface like this, right? And another part of the light gets refracted inside the thin film, right? So when beam of light is instant on the top surface of the thin film, it is divided into two parts. A part of the light is reflected, okay, from the top surface of the thin film, and the remaining part gets refracted inside the film. And this refracted ray strikes the point B at its bottom. Right? And this refracted ray also divided into two parts. Right? One part is reflected, okay, inside the film, and another part of the light is emerges out or transmitted out from the thin film, right? So this is a refracted ray. When this refracted ray strikes the bottom of the thin film at point B, it is divided into two parts. One part is reflected in the denser medium itself, the thin film itself, and the second part is transmitted out from the film, right? And this reflected ray is strikes on the top surface of the thin film at point C. Right? And it is also divided into two parts. One part is gets refracted from the surface like this, and another part gets reflected inside the thin film. Right? And this reflected ray is instant at the bottom surface of the thin film at point D. Again, it is also divided into two parts. One part gets reflected and another part is transmitted. This reflected ray strikes at point E, and it is also, some part is refracted and another part is reflected like this. Right? And one part gets reflected and another part is transmitted out. Okay, from the point F. Right? So similar way this process is going on. Right? Until the energy of the light fall below some critical value. Right? So that is, there is a multiple reflection takes place inside the thin film. So this type of multiple reflection takes place until the energy of the light fall below the critical value. So otherwise this process will continue. Right? Okay, here the ray which are the rays from the point A, C and E are appears to be reflected from the top surface of the thin film, right? The rays which are coming from the point A, C and E are appears to reflected from the top surface of the thin film, right? So that is why they are called reflected waves or reflected rays. Reflected waves, because these rays are appears to be reflected from the top surface of the thin film, right? And the rays from the point B, D, F, these three are appears to be transmitted from the bottom surface of the thin film, from the bottom surface of the thin film. So that is why they are called transmitted rays or transmitted waves, right? So these are reflected waves and these are transmitted waves, right? So here both the reflected waves and the transmitted waves produce interference. Both the reflected waves and the transmitted waves produce interference. Result, there will be a alternate bright and dark fringes are formed. Alternate bright and dark fringes are formed. So such a fringes are called interferent fringes. Interference fringes. Right? When these transmitted rays travels along this direction and they are superimposed to each other or interfere with each other at various points, so there will be an alternate bright and dark fringes are formed. So such a fringes are called interferent fringes. Interferent fringes. So both the reflected waves and the transmitted wave produce interference. First we go for the interference due to transmitted waves. Interference due to transmitted waves. Right, first interference due to transmitted waves, right? So for that, let us consider only two transmitted waves. One is from the point B and another one is from the point D, right? So just let us consider two transmitted waves from the point B and D, right? So these two transmitted waves are moved together up to in this region, that is in the region AB. That is both transmitted waves from the point B and D are combined and move together. Where? In the region AB. Right? When this light is incident at point B, that two transmitted waves are divided. Right? So one transmitted wave is transmitted along this direction, and another transmitted wave is travels along BC and then along CD, and then it is emerges out from the thin film. Right? So one transmitted wave travels from the point B in this direction, and another transmitted wave from the point D travels along BC direction and then CD direction, and finally it is emerges out. Right? Okay, but actually these two transmitted waves are single. Where? In the region AB. Okay, so before splitting, these two transmitted waves are single and they are moved together with the in phase. After splitting, one of the transmitted wave is a travel in this direction, and another transmitted wave is a travels along BC and then CD and emerges out from the thin film. Right? Okay, here the transmitted wave from the point D travels extra path. The extra path travelled by the transmitted wave from the point D is extra path travelled by the transmitted wave from the point D is BC plus CD. When we compare it to the transmitted wave from the point B, the transmitted wave from the point D would travel extra path. The extra path travelled by this transmitted wave is BC plus CD. So extra path is equal to BC plus CD. Right? Suppose, just you assume here the ray of light is incident on the top surface of the thin film with an angle of incidence I. With an angle of incidence I. Suppose this ray of light is incident on the top surface of the thin film normally. Suppose this light is incident like this. Suppose if the light is incident on the surface normally for normal incidence, angle of incidence is equal to 0 and angle of refraction value also 0. The angle of incidence and the angle of refraction values are 0 when the light is incident on the top surface of the thin film normally. Right? Suppose let us assume the light is incident on the surface normally. Right? For normal incidence, the point B and D are very close to each other. Right? So this point becomes here. Okay? So the light BC is travels along this direction, and once again it gets reflected along CD direction like this. Right? If the light is incident normally, the point B and D are very close to each other, then the distance BC and CD is almost equal to the thickness of the thin film. So this is very important condition. Just to listen, my dear students. When the light is incident normally, the point B and D are very close to each other. So the distance BC, this distance BC becomes here, and the distance CD becomes here. So the distance BC and CD is almost equal to the thickness of the thin film. Right? So BC is equal to CD is equal to the thickness of the thin film. Right? Then extra path traveled by the transmitted wave from the point D is extra path equal to D plus D. That is equal to 2D. The extra path traveled by the transmitted wave from the point D is 2D. Right? We know that the distance traveled by the light in air medium, is equal to mu times of the distance traveled in denser medium. Right? So it is very familiar this. The distance traveled by the light in air medium is equal to mu times of the distance traveled by the light in the denser medium for a given time. Right? Here the transmitted ray from the point D actually travels in the denser medium. So therefore the optical path covered by the transmitted wave from the point D is optical path covered by the one of the transmitted wave from the point D is becomes 2 mu D, because this transmitted wave is travels in the denser medium. So optical path traveled by this transmitted wave in the denser medium is given by 2 mu D. Right? So this is the path difference, that is optical path difference between these two transmitted waves. So optical path difference between the transmitted waves from the points B and D is 2 mu D. So generally path difference is denoted by the letter del. Right? So optical path difference between the transmitted waves from the point B and D is 2 mu D. Generally optical path difference is denoted by the letter del. So this is path difference between the transmitted waves. Right? Now we go for condition for brightness and darkness. So whenever the transmitted waves are interfere to each other, there will be alternate bright and dark fringes are formed. If bright fringes are formed, then the interference is called constructive interference. If dark fringes are formed, then the interference is called destructive interference. Right? We know that for constructive interference constructive interference. Condition for path difference. Condition for path difference. Condition for path difference, del is equal to n lambda. So condition for path difference, that is for constructive interference, the condition for path difference is del is equal to n lambda. Del is equal to n lambda. Right? For transmitted rays, for transmitted waves in the thin film, the condition for constructive interference, because already path difference between the transmitted waves is derived, that is 2 mu d. So for transmitted waves in the case of a thin film is 2 mu d is equal to n lambda. So this is general condition for constructive interference, that is for path difference for constructive interference, del is equal to n lambda. In the case of a thin film, the path difference between the transmitted waves is obtained, that is 2 mu d. Therefore, condition for constructive interference in the case of transmitted waves is 2 mu d is equal to n lambda. 2 mu d is equal to n lambda. Right. Here, what is mu? The refractive index of the thin film. What is the d? Thickness of the thin film. What is n? Order of bright fringes. N is order of bright fringes. Bright fringes. Its value is 0, 1, 2, 3, and etc. Right? And what is the lambda? The wavelength of the incident light. Wavelength of the incident light. So lambda is the wavelength of the incident light, and mu be the refractive index of the thin film, d thickness of the thin film, where n order of bright fringes. Its value is from 0 to infinity. 0 to infinity. Right? Okay. And for destructive interference. For destructive interference, condition for path difference. Condition for path difference, del is equal to 2n minus 1 lambda divided by 2. Okay. Condition for path difference in the case of constructive interference, del is equal to n lambda. This is general condition. And condition for path difference in the case of destructive interference, del is equal to 2n minus 1 lambda divided by 2. 2n minus 1 lambda divided by 2. So for transmitted waves, condition for destructive interference. Okay, condition for destructive interference, the path difference obtained is 2 mu d. So 2 mu d, which is equal to 2n minus 1 lambda divided by 2. Right? For destructive interference, the condition for path difference is del is equal to 2n minus 1 lambda divided by 2. In the interference due to transmitted waves, the path difference between the transmitted wave is derived, that is del is equal to 2 mu d. Del is equal to 2 mu d. Substitute del is equal to 2 mu d, then this condition becomes 2 mu d is equal to 2n minus 1 lambda divided by 2. So this is condition for destructive interference in the case of transmitted waves. So this is condition for destructive interference. This is condition for constructive interference in the case of transmitted waves. Right? Already I told mu refractive index of the medium, that is thin film medium, and d thickness, and n order of dark fringes. Right? Its value 1, 2, 3, and etc. Right? In the case of interference due to transmitted waves, the order of dark fringes is 0, 1, 2, 3, and etc. Right? That is 0th order also possible in the case of interference due to transmitted waves. But dark order is not possible. So that is why here n is the order of dark fringes, and n value is from 1, 2, 3, and etc. So condition for constructive interference is 2 mu d is equal to n lambda, and condition for destructive interference 2 mu d is equal to 2n minus 1 lambda divided by 2. So far we discussed about the interference due to transmitted waves. right? So in this case, the condition for constructive interference is 2 mu d is equal to n lambda, and the condition for destructive interference is 2 mu d is equal to 2n minus 1 lambda divided by 2. 2n minus 1 lambda divided by 2. So next we go for interference due to reflected waves. Interference due to reflected waves. Interference due to reflected waves. Right. Before going to this, we should know one important condition, right? In the case of, in the topic interference. Okay, that is, if any wave travels in the rarer medium and gets reflected from the surface of the denser medium, right? Suppose this is glass plate. A light or wave travels in the air medium. So air medium is the best example for rarer medium. Rarer medium. And this is glass. Glass is one of the example for denser medium. If any wave travels in the rarer medium and gets reflected from the surface of the denser medium, okay, and there is additional path change of pi, and phase change of pi and path change of lambda divided by 2. Okay, a wave travels in the rarer medium, gets reflected from the surface of the denser medium, undergoes a phase change of pi and path change of lambda divided by 2. So this is a very important condition while dealing with the interference region, right? So once again I repeat, if any wave travels in the rarer medium and gets reflected from the surface of the denser medium, automatically undergoes a phase change of pi or path change of lambda divided by 2. Right? So this is important condition and keep it in your mind, right? Okay, now we go for interference due to reflected waves. Right? Now consider only two reflected waves in this diagram. One is from the point A and another one is from the point C. Right? So just you consider these two reflected waves which are coming from the points A and C. From the points A and C, right? Okay, so here this reflected ray or wave is actually travels from the point A to B and then B to C, right? And finally it is comes out from the top surface of the thin film, right? But this reflected ray is directly reflected from the point A on the surface of the top surface of the thin film, right? So here, what is the extra path traveled by the reflected wave from the point C? Okay, the extra path traveled by the reflected wave from the point C is AB plus BC. So extra path traveled by a reflected wave from the point C is AB plus BC. Right? Okay, once again, if the light is incident on the surface normally, the point A and C are very close to each other. So the length AB and BC becomes equal to the thickness of the thin film. Right? Okay. So only this condition is only applicable for normal incidents. If the light is incident on the surface normally, the point A and C are very close to each other. So the line AB and BC value becomes equal to the thickness of the thin film. Suppose let us assume the light is incident normally. So therefore AB and BC value is thickness equal to the thickness of the thin film. Right? That is for normal incidents. Okay, AB and BC is equal to the thickness of the thin film. Thickness of the thin film, right? Therefore, extra path traveled by the reflected wave from the point C becomes d plus d, that is equal to 2d. That is equal to 2d, right? Here, this reflected wave actually travels in the thin film medium itself. It is travels in the thin film medium itself. So the optical path traveled by this wave, reflected wave, is optical path. Optical path is nothing but mu times of the distance traveled in denser medium. That is optical path. So optical path is mu into 2d or 2 mu d. 2 mu d. This is optical path. Right. So this optical path traveled by the reflected wave from the point C is nothing but the path difference or optical path difference between these two reflected waves. So optical path difference between the reflected waves from the point A and C is 2 mu d. 2 mu d. So optical path covered by the transmitted wave from the point C is 2 mu d. That value is equal to the path difference between these two reflected waves. Okay, these two reflected waves, right? And one more thing, here this reflected wave actually travels in the rarer medium and gets reflected from the surface of the denser medium. Okay, but this reflected wave is coming from the bottom surface of the thin film. That is, the light travels in the denser medium and gets reflected from the surface of the denser medium. So it does not suffer any phase change or path change. But this reflected ray actually travels in the rarer medium and gets reflected from the surface of the denser medium. So it automatically undergoes a phase change of pi and path change of lambda by 2. Right? So one of the reflected wave travels in the rarer medium and gets reflected from the surface of the denser medium. It suffers a additional path difference of or additional path change of lambda by 2. So additional path is equal to lambda by 2. Okay, actual path difference between these two reflected wave is 2 mu d, and here this reflected wave actually travels in the rarer medium and reflected from the surface of the denser medium. It suffers a additional path change of lambda by 2. Right? What is the total path difference between these two reflected waves? So total path difference between the two reflected waves from the point A and C is equal to actual path difference of 2 mu d plus additional path difference lambda by 2. Additional path difference lambda divided by 2. So this is total path difference between the reflected waves in the thin film. So del is equal to 2 mu d plus lambda by 2. Right? In the case of a transmitted wave, the path difference between the transmitted waves is just del equal to 2 mu d. For reflected waves, the path difference between the two reflected waves is del is equal to 2 mu d plus lambda by 2 plus lambda divided by 2. Right? Now we go for constructive interference and destructive interference condition. Right? For constructive interference, path difference del is equal to n lambda. Path difference del is equal to n lambda. For reflected waves, path difference del is equal to 2 mu d plus lambda by 2. 2 mu d plus lambda by 2. Right? Therefore, 2 mu d plus lambda by 2 is equal to n lambda. 2 mu d plus lambda by 2 is equal to n lambda. So this is one of the condition for constructive interference in the case of reflected waves. Right? Suppose if the lambda by 2 is taken this side and this condition becomes 2 mu d is equal to n lambda minus lambda by 2. If lambda by 2 come from left side to right hand side, the plus lambda by 2 becomes minus lambda by 2. Minus lambda by 2. Right. So 2 n lambda minus lambda divided by 2. Divided by 2. Right. Here lambda common, so take outside. So okay, 2n minus 1 into lambda divided by 2. So 2 mu d is equal to 2n minus 1 lambda divided by 2. 2n minus 1 lambda by 2. So this is another condition for constructive interference in the case of reflected waves. So this is main one. 2 mu d plus lambda by 2 is equal to n lambda. If the lambda by 2 is taken to this side, and this equation becomes 2 mu d is equal to 2n minus 1 lambda by 2. So both equations are condition for constructive interference in the case of reflected waves in the thin film. Right. Okay, mu refractive index of thin film, d thickness of the thin film, and n order of bright fringes. N is order of bright fringes. Order of bright fringes. Its value is 0, 1, 2, 3 and etc. Right? So condition for constructive interference in the case of reflected waves, 2 mu d plus lambda by 2 is equal to n lambda, or 2 mu d is equal to 2n minus 1 lambda by 2. Right? Lambda wavelength of the incident wave. Here n is the order of bright fringes. Its value 0, 1, 2, 3 and etc. 1, 2, 3 and etc. Right. Similarly, the condition for destructive interference. Destructive interference, del, path difference del is equal to 2n plus 1 lambda divided by 2. Okay, whenever the additional path difference, that is lambda by 2, is introduced in the interference region, the condition for destructive interference, the path difference should be taken as del is equal to 2n plus 1 lambda divided by 2. Otherwise, for destructive interference, path difference del is equal to 2n minus 1 lambda by 2. Right? Here, additional path difference lambda by 2 is introduced here. So, in this case, for destructive interference, path difference should be taken as del is equal to 2n plus 1 lambda divided by 2. But in the previous case, that is for transmitted waves, there is no additional path difference. So that is why the condition for path difference is taken as del is equal to 2n minus 1 lambda by 2. Here, additional path difference is introduced here. So that is why the path difference del is equal to 2n plus 1 lambda by 2. In which interference? Destructive interference. Destructive interference. Right? Path difference is 2 mu d plus lambda by 2. 2 mu d plus lambda by 2. So 2 mu d plus lambda by 2 is equal to 2n plus 1 lambda by 2. Right? So this is a condition for destructive interference in the case of reflected waves. Right? If lambda by 2 is taken to this side, 2 mu d is equal to, just you multiply lambda by 2 in this two term. So 2n into lambda by 2 plus lambda by 2. So 2 cancel. And this lambda by 2 becomes minus lambda by 2. 2n into lambda by 2 plus lambda by 2. This lambda by 2 is taken to this side, positive becomes a negative, so minus lambda by 2. So plus lambda by 2 minus lambda by 2 cancel. So 2 mu d is equal to n lambda. Right? So these two are condition for destructive interference in the case of interference due to reflected waves. Reflected waves, right? Here what is n? Order of dark fringes. Here n is order of dark fringes. And this value also 0, 1, 2, 3 and etc. Right? Order of bright fringes also 0, 1, 2, 3 and etc. And order of dark fringes also 0, 1, 2, 3 and etc. So both conditions are possible in the case of interference due to reflected rays. Interference due to reflected rays. So condition for destructive interference for reflected waves is 2 mu d plus lambda by 2 is equal to 2n plus 1 lambda by 2. Okay, if lambda by 2 is taken to this side, after simplification we can get 2 mu d is equal to n lambda. 2 mu d is equal to n lambda, right? So these conditions are introduced by assuming the light is incident on the surface normally. The light is incident on the surface normally, right? The light is incident normally. Incident normally for reflected waves, for transmitted waves, condition for constructive interference, condition for constructive interference, 2 mu d is equal to n lambda. 2 mu d is equal to n lambda. Condition for destructive interference, 2 mu d is equal to 2n minus 1 lambda divided by 2. 2 mu d is equal to 2n minus 1 lambda divided by 2 for transmitted waves, right? For reflected waves, condition for constructive interference, 2 mu d plus lambda by 2 is equal to n lambda, or 2 mu d is equal to 2n minus 1 lambda by 2. 2n minus 1 lambda by 2, right? Condition for destructive interference, 2 mu d plus lambda by 2 is equal to 2n plus 1 lambda by 2, or 2 mu d is equal to n lambda. 2 mu d is equal to n lambda, right? So these conditions are only possible if the light is incident on the thin film normally. Okay, normally, right? Other than normal incident, suppose light is incident on the surface of the thin film with an angle of incidence I. Okay, that is angle of incidence I is not equal to 0. Right? If the angle of incidence is not equal to 0, then angle of refraction also not equal to 0. Angle of refraction also not equal to 0. Right? In that case, the condition for constructive interference and destructive interference for transmitted waves, and the condition for constructive interference and destructive interference for reflected waves, there is a slight changes should be introduced. That is, instead of 2 mu d, we should write 2 mu d cos r. Right? If the angle of incidence is equal to 0, the angle of refraction value also 0. In that case, condition for constructive interference, so 2 mu d is equal to n lambda for transmitted waves. And condition for destructive interference, so 2 mu d is equal to 2n minus 1 lambda by 2 for transmitted waves. Okay, other than normal incidence, the condition for constructive interference in the case of transmitted waves becomes 2 mu d cos r is equal to n lambda. 2 mu d cos r equal to n lambda. And this equation becomes 2 mu d cos r is equal to 2n minus 1 lambda divided by 2. Just 2 mu d is replaced by 2 mu d cos r. Here also 2 mu d is replaced by 2 mu d cos r. If the angle of incidence is not equal to 0. If the angle of incidence is equal to 0, just 2 mu d, no need of a cos r. Right? Similarly, condition for constructive interference and destructive interference in the case of reflected waves becomes 2 mu d cos r plus lambda by 2 is equal to n lambda, or 2 mu d cos r is equal to 2n minus 1 lambda divided by 2. 2n minus 1 lambda divided by 2, right? Similarly, condition for destructive interference, 2 mu d cos r plus lambda by 2 is equal to 2n plus 1 lambda by 2 plus 1 lambda by 2, or 2 mu d cos r is equal to n lambda. 2 mu d cos r equal to n lambda. So these two are condition for destructive interference in the case of reflected waves if the angle of incidence is not equal to 0. And these two are condition for constructive interference for reflected waves, okay, if in the angle of incidence is not equal to 0. And for a transmitted waves, condition for constructive interference, 2 mu d equal to cos r equal to 2 mu d cos r equal to n lambda. For destructive interference, 2 mu d cos r equal to 2n minus 1 lambda by 2. If angle of incidence is not equal to 0, 2 mu d is replaced by 2 mu d cos r, right? So this is for about interference in thin films, right? Okay, so the topic over. My dear students, just to go through this topic properly with 100% concentration. If you have any doubt, just to call me, right? Thank you, students. We will see in the next class.